Standard video games use pre-recorded animation clips triggered by player input. The character's model follows a script rather than calculating the physical forces involved in a jump or a tumble. I wanted to move beyond mimicry. I wanted to see if an artificial neural network could learn the complex laws of physics from scratch without any visual guides to follow. This diagram shows the digital dummy we used inside the Mujiko physics engine. We gave it a body with real joint limitations, the ability to generate raw torque, and subjected it to an active downward gravity vector. We stripped away every pre-programmed animation and guiding script. The AI started with absolutely no instructions on how a human body is supposed to move. Without the safety net of animation, the AI was stranded in a void. It had to organically deduce the laws of physics on its own, or fail completely. Dropping an untrained digital brain into a high-fidelity physical simulation produces immediate, chaotic results. Because the AI has no concept of how its motors work, it fires random, uncoordinated electrical signals to its simulated limbs. This video shows the consequence of that guesswork. Gravity instantly overpowers the system, causing the dummy to violently spasm, twitch, and collapse into a heap. To build structured learning, I introduced the Proximal Policy Optimization Algorithm, or PPO. The loop is simple. The AI acts, observes, and iterates to filter out falls. The system assigns a positive reward only when the dummy stays upright and achieves forward motion. After 10,000 trial and error iterations, the twitching stopped. The AI realized it had legs. It began throwing its shoulders down and lunging forward, using its limbs to catch its balance. The algorithm transformed a generator of chaotic noise into a functional digital toddler, capable of fighting gravity to remain upright. A stumbling toddler is a start, but we wanted to see if the AI could develop the coordination of an elite gymnast. Basic survival algorithms rarely produce a backflip because the move requires the AI to intentionally throw itself off balance, the opposite of staying upright. To achieve this, I manually adjusted the physics engine's reward function, the system that defines what the AI perceives as success. We overlaid a rotational axis on the body, tying success to the speed of backward spin. Next, a z-axis graph tracks jump height. Both metrics feed into a single gauge, creating a feedback loop strictly rewarding the physical mechanics required for a backflip. By prioritizing these specific data points, the AI learns that maximizing backward rotation is the only way to satisfy its internal scoring system. The AI trained under these modified rules for 100,000 simulated lifetimes. It is a repetitive process of pitting a learning agent against physical constraints, forcing it to adapt through millions of failures. Eventually, the dummy achieves its goal. It launches backward into the air, executes a tight rotation, and outmaneuvers gravity to land firmly on its feet. The AI calculates the torque needed for every joint in real time, counteracting gravity through pure computation rather than following a script. This represents true kinetic intuition, the learned ability to coordinate a physical body in three-dimensional space. Moving this logic to a physical robot requires accounting for real-world hardware friction and sensor noise. However, the core proof remains. Neural networks can deduce complex coordination without human scripts. This suggests a path toward machines that learn to navigate our world through their own experience rather than rigid